Greetings. Yep, okay, we're good. Chem Review, Semester 1, Final Exam, 2018. What you guys are going to get is a formula sheet that's front and back, full of formulas, full of information, in addition to your periodic chart. That's why it says Honors/Chem Final Exam Semester 1, because you and HChem are getting the exact same thing. So, first things first, you got your valence electrons around the atoms, so you can do Lewis dot structures. Something we did not mention, we talked about the idea of calculating percent error, okay? We have done that in the lab. I can reasonably guarantee you that would be in the multiple choice section if we were to have something like that, because I did not put that in the lab portion review. That's okay, all right? So for that, you have accepted and measured. Okay, measured is what you counted, you measured in the experiment. Accepted is the actual number, what is accepted. So, for example, if the accepted value is 4 and you measured 3, it doesn't matter what, and the accepted is 4, it's 4 minus 3. Now, keep in mind, these are absolute value bars, so your number is going to be positive. It doesn't matter if this is going to be negative or not, okay? That's a key thing. So 4 minus 3 is 1. 1 divided by 4 times 100 gives you a 25% error. So that's what it would look like. Okay? So once again, for percent error, you have the formula. Measured is what you got, accepted is what's the true value. The top part, it's always going to be a positive number. Even if you subtract here and it becomes negative. You multiply by 100, and that's what I showed you here, and you have 25% error in this example. Okay, I do need to move on, okay, as we go through here. Density equals mass divided by volume. It's there. Okay. Electronegativities. Again, this is a question of electronegativity. How badly does an atom want the electron from another atom? Okay. The higher the number, the more it wants it. The lower the number, it's not so interested. Not really. Okay. So you're going to if you're going to go and compare something like lithium and fluorine, LiF, you would take 4 minus 1 and you get a difference of 3. Then you look down here and say, okay, here's my chart. My number is 3. 3 is bigger, greater than 1.7, so that's an ionic bond. Okay? Guys have done this before. Okay, the other things you needed. I gave you guys the metric conversions if you need it. I do not think I don't believe I did any metric conversion problems with you guys, so I'm not going to worry too much about it. But it's there to help you remember. Here's the temperature conversion formulas from Celsius to Kelvin and Kelvin to Celsius. Again, don't worry about the Fahrenheit. It's there. It's part of the graphic. Okay, because I thought this looked a lot nicer than what I could have typed up. Okay, and that is your formula sheet front and back for this. So let's go ahead and let's spend our time taking a look at the chapters as we are moving onward with this. Okay, let's go with 125%. All right. So we talked about the idea of chapter 1, creation mandate. What is it? Where do you find it? Okay, think. What is it God wants man to do? Where would you find that in the Bible? Scientific models, what are they? What are they used for? Remember, scientific models, they help us try to help us explain, to help us understand what scientists are observing. A model, it could be a computer model, it could be a picture, it could be a diagram, it could be a three-dimensional thing. So models can look different ways, okay? Chemistry first taught as an academic discipline, that one's in your notes. Biblical worldview, what is it? Again, the idea that you're based, how you view the world based off of the scriptures themselves. Quantitative, qualitative, we already talked about that. Here's two examples of that. Scientific method, yeah. Knowing the difference between a theory and a hypothesis, absolutely. Theory has some more data to back it up. It's not completely accepted, whereas a hypothesis, it's a proposed explanation, okay? When we look at observation, well, what is it that we're noticing when we do a lab experiment? What is data? Give two examples of data, okay? Now, when we are doing things like experimental group, control group, independent variable, dependent variable, real fast. The control group, when you're testing for something, the control group, you leave it alone. You don't do anything to it. Okay, so you have an example here. I'll let you read the example. The experimental group is the one that you are messing around with to test out this variable. The variable could be something like extra water or extra fertilizer, or you've poured acid into it. It depends. Okay, but you're testing for one variable. Now, the dependent variable, okay, the dependent variable is what the results you are looking at. In other words, if I'm saying I want to know the effects of carbon, if I add it to the soil, how does that affect plant growth? The dependent variable is how tall the plants grow, because that's where we're going to see, is it legit or not? So the dependent variable has to do with what your outcome, what's your data going to look like? So in this case, how tall the plants are, okay? Independent variables are things that don't get altered, like the amount of soil, the amount of water that you give in a plant experiment. Those are independent variables, okay? Chapter 2, ex nihilo, that's in the notes. Density, we talked about chemical property, physical property. Okay, so if you think about it, physical property is something that's affecting the physical aspect of water. Like water is clear, gold is yellow. Those are physical properties. Chemical property would be something where you're looking at how it affects, okay? Gold will dissolve in acid. That's an example of a chemical property, okay? Conductivity, we already know. Ductility, malleability, luster, physical change, chemical change, okay? Physical change, remember, you start out with a substance, you still end up with the substance. Piece of paper, folded in half, oh look, physical change. A chemical change is when you start out with paper and you end up with something else. I light the paper on fire, it burns to a carbon. Okay? All right. Mixtures, homogeneous, heterogeneous, suspensions. I'm going to let you guys read on that. Okay. You should be able to identify these as diatomic, monatomic. Okay. We already went over this, so looking onward here. So when we talk about an ion, ladies and gentlemen, we're looking at, is it a positive or a negative charge? Anions are negative, cations are positive. So when we look at these here, which of the following would be considered an ion? Anything that is a negative or a positive charge. So hydrogen's an ion, O2 is not, silver is, sulfur is, boron, no, NH3, no, there's no positive or negative, and NH4 plus. Entropy, we talked about it. We talked about Kelvin, okay, let's move on. We went into now chapter 3, okay, that's pretty straightforward. I went over percent error with you guys. You have a percent error problem, so you can practice that. Accuracy and precision, real fast. Precision is how close your measurements are. Accuracy has to do with how close are you to the true value. So in this case here, we look at these, and here's our true number. They're precise because the numbers are pretty close to each other, and they are accurate. When we look here, notice here's our accurate number, our true number, but if you look at these measurements, they're nowhere near it. There's no precision because they're not close to each other, okay? And they're way off the true number. So that's not precise, it's not accurate. Okay? I gotta look at my timing here. All right, law of definite composition, using water as an example. When we look at composition, the idea is, what is something made up of? Water, we know it's hydrogen and oxygen. Definite means it's very specific. There's no difference, that's it. So for this, for definite composition, we can look at, there's 2 hydrogens to every 1 oxygen. That's definite composition. So if I look at like so many grams of water, 16 grams of water, okay, let me start, 18 grams of water, 2 grams are based off of hydrogen, and then 16 is off the oxygen. Don't panic about the masses, but you should know the numbers. It's a definite thing, it's fixed. Okay, this is a fixed thing. If you have 1 drop of water or a swimming pool filled with water, okay? Electron, proton, neutron, you should know that. The A number, Z number, okay? Keep in mind, if I'm looking at something like hydrogen, the Z number is your atomic mass, okay? Your A number is your atomic number, which is how many protons you have. So here, that 2, you have 1 proton and 1 neutron. Here, you have 1 proton. How do I know how many neutrons I have here? You subtract the smaller number from the larger number, okay? So if you look at it, that's what it would look like. That's the arrangement of the A and the C. Okay. Looking at these guys here, you should know them. You should know them. They're there, how electrons are arranged, okay? Hund's rule, think about that monopoly rule, okay? Electron configuration, you guys should know that. The 4 parts of the electron's address, remember, your basic energy level, the sub-level that it's going to be in, where in that sub-level it is, and then the spin, okay? SP, D, and F orbitals, okay? You should know how many electrons fit into S2, P6, D10, F14, okay? Electron configuration, what does that look like? These are electron configurations in order, like 1s2, 2s2, 2p6, something like that. So in this case here, which is the following is correct for nitrogen, for 7 electrons, the easiest way to do this is look at the number up here, okay? If I have 1s2, the 1 is the principal energy level, the S is your sub-level, the 2 is how many electrons you've got in there at that moment. So you're going to take these numbers here and you're going to add them up to get 7, okay? And I will let you figure that one out. I'm trying to move fast and hit the high points. All right. HE. What are we talking about here? If I look at something like HE, it's saying to me, instead of writing 1s2 every single time, I would write HE 2s2 2p6. So that's what they're saying. This is a noble gas configuration, which for HE, it's not that big of a deal. But when you're looking at something like neon, okay? 1s2, 2s2, 2p6, okay, 3s1. So I have 11 electrons there, 2 plus 2 plus 6 plus 1. That's 11. That gives it to me for sodium. This is the long way of doing it. But since I know that this is neon, that's where the abbreviation comes in. It's easier to write it this way than this way. Do you guys see the difference? It's the same thing. They're both sodium. Sodium has 11 electrons in there. Okay? Again, I got to look at time because, okay. Isotopes. Isotopes, you can tell things like carbon 12, carbon 13, carbon 14. What's up with that? Same element, same number of protons, because remember, the identity of the atom is based off of the protons. Different number of neutrons, so that makes the atom weigh a little bit more. Well, what about electrons? They're so tiny we don't look at it when we look at the weight of the atom, because electrons are so tiny. So isotopes, same protons, different neutrons, they weigh differently. Okay? All right. So when we look at something like, all right, carbon has 6 electrons. Okay? So carbon has 6 electrons, right? We know that in our first level, our 1s2, we got 2 electrons that are there. Then in our second level, we have our 2s2 and then 2p2. I'm using the Bohr model. Valence. Valence electrons, guys. Valence electrons are all these outer electrons. That's where the action is happening when atoms join together. That's where it's happening, nowhere else. So carbon has 6 electrons. 2 are in the very center next to the nucleus, and then the 4 on the outside, which allows it to hook up with almost anybody. Carbon is very easy to hook up because it's just got 4 electrons. It can either give up 4 or pick up 4. It depends what's needed. But if carbon has 6 electrons and has a charge of 0, okay, the moment an electron is lost, remember an electron is a -1 charge, the kind of charge it'll have is a +1 charge. That's the thing about carbon, okay? You usually don't see it that way, but for my example here, that'll work. And again, if I put this up on YouTube, then you guys can pause it and rewind and go from there. Okay? Now, so PO43-, is that one atom? Is it an ion? Is it an element? Or is it an isotope? This is an ion, a polyatomic ion, to be specific. Okay, let's move on here. I already covered a lot of stuff. Energy, potential, and kinetic. Potential is stored up energy. Energy ready to go, but it's not active. Kinetic energy is active energy, running around. A ball dropping off a cliff. Something being lit on fire. If you got a piece of paper that's, you light it on fire, you got some kinetic energy happening here. Okay, I'm just rapidly going through here. Periodic table history, knowing like Mendeleev and Moseley probably would be a good thing. Periodic trends would be a good idea to know. Again, those are in your notes. Okay. Especially like atomic radius, electronegativity, okay, when you look at those. All right, we talked about polar covalent, non-polar covalent bonding. Remember, we went back to this to determine if something was polar or non-polar covalent or ionic.